Welcome back. In this video I'm going to introduce how we can statistically test whether two categorical variables are associated. And then I'm specifically going to focus on the chi-squared test, which is the most commonly test used in this kind of situation. So to put this into context, so far we have mostly looked at linear models. And linear models are all about figuring out how a continuous outcome variable is predicted by other variables. In the case of linear regression, those variables can be of any kind. In some special cases like the t-test, we might care about how a grouping variable influences a continuous outcome. However, those techniques break down when we're actually interested in two categorical variables. So if we're wondering whether different nationalities have different preferences for ice cream, or whether some categorical factor, such as gender, ethnicity, profession, influence party choice, in those cases we need a different way of thinking about the statistical problem. And for that we need to figure out what the hypothesis is that we are actually wanting to test, then what the null distribution is, and how we can test whether the data we observe is significantly different from that null distribution. So let's go through the ice cream example in quite a bit of detail to think about these different steps. So if we were interested in whether Brits and Italians have different preferences for vanilla versus chocolate ice cream, we might just go and ask a bunch of people and basically figure out in which of these four categories they belong. With these observations, it now seems that a lot of British people like vanilla ice cream. Not that many Italian people like vanilla ice cream. Is that evidence of a difference in preferences between the two categories? Well, possibly not if we start looking at the number of people that there are overall in each row and in each column. Because in this particular sample we only have 10 Italians and 20 British people. Now our hypothesis is that taking into account the total number of people in each row and in each column, that taking that into account the distribution between the cells still differs. So the null distribution is not that the same number of people are in each cell, but it's something slightly more complicated, where we need to take the number of chocolate ice cream lovers overall and the number of British people overall into account. So how do we actually do this? How would we create a null distribution? Well, we need to figure out the probability of a person being British and the probability of a person liking chocolate ice cream, and then multiply those two together. And that's then the probability that a person, if there is no relationship between those two, would have of being a British person who likes chocolate ice cream. And then we just multiply it by the number of people we have in our sample. So doing that in this particular case would give us 8 people who like chocolate ice cream and are British. We can do the same thing for the other 3 boxes. And now I have a null distribution. This looks a bit different from the hypothetical sample we observed. If we now put both sets of numbers into the same table, we can start comparing them. So we can now see that while we observed 14 British people who liked vanilla ice cream, in fact, there are only 12 that we would have expected to see in that cell under the null hypothesis. Likewise, we actually observed 6 Italians who liked chocolate ice cream. Under the null hypothesis, we would have expected only 4 to be in that cell. Now, how far away is our data from the null hypothesis? It's not entirely obvious how we would calculate this. So the first step might be to just add up the differences in each cell. Unfortunately, that doesn't work, because they have to sum up to 0. We could add up the total, the absolute differences. So in that case, in each of the cells, there's a difference of 2 between the observed and the expected number. So we could do this. We would arrive at 8 and we could say, well, our observation is 8 people away from the expected null distribution. However, this is not ideal because it depends on the sample size, and it also doesn't take into account that being 2 people away might be differently important, depending on whether you're 2 people away in a huge cell or 2 people away in a small cell. So to overcome this, we have the chi-squared statistic that actually looks rather complicated in this formula. But basically, all that we're doing is we're taking the difference in each cell, we're squaring it to get a positive number, and then we are dividing it by the expected count to roughly get a size of the difference in relation to what we expected in that particular cell. So we do it in this example, we have a chi-squared value of 2.5. You don't need to remember the formula, but you should have the intuition. So what we're doing in chi-squared is we're calculating how far our observed data is from the expected data under the null hypothesis. And to calculate it in a way that takes into account the size, the expected size of each cell, and gets rid of the sample size. Quite often you'll notice that in such a small sample like this one, something called the Yates correction is used, and you get a different chi-squared value. But that's an exception to the rule. If we now say, well, our chi-squared is 2.5, what do we do with that? Well, we need to do hypothesis testing. We need to say, how likely is this observed chi-squared value to arise if there is no difference in the preferences of Italians and Brits? One way that we can always go down is we can simulate it. Here I run 1,000 simulations of this experiment. We can see the distribution of these 1,000 chi-squared values that are not continuous, since we can only be whole people off in the cells. We see, well, our particular value of 2.5 actually showed up in almost 20% of the situations. So in 23% of the situations, we would have observed a deviation as large as the one that we had, or larger, under the null hypothesis. So clearly we would conclude our observation does not give us evidence that there is a significant difference in ice cream preferences. That would be the simulation route. We can just use the chi-squared test function in R, but that's not great, because it assumes that the chi-squared statistic would be continuous, which it clearly isn't. So in this particular case, it gives us a p-value that's about half of what it should be. So that's not a great thing to do when you are in a situation where chi-squared is far away from being continuous, so where you have a small sample. Still, this would agree that there's no significant difference. For such a small sample, we are better placed with allowing R to apply the Yates correction. With that, we get a p-value that's actually quite similar to the simulated value. However, the Yates correction is a bit complicated and contested, so what I would highly encourage you to do is to actually use simulations, which you can very easily do by just literally telling R to run the simulation. So the chi-squared test function has a simple parameter to ask for the simulation, and there we get exactly the same result as we got in the manual simulation I ran before, and it's very transparent how that result was obtained. When you have a larger sample, there is no big difference usually between the simulated result and the estimated result. But still there's nothing wrong with simulating it, because then that actually uses only the data we have at hand to figure out how likely we would have been to observe that data without a specific difference between the different cells. So be careful with chi-square tests to small samples and consider using simulation. Let's look at another example that introduces a couple of new important points. So in the case before, we had two variables with two categories. We might be interested in a situation where we still have two variables, but we have more categories. So we ask about party affiliation. Does party affiliation vary by gender? And we have three categories: Democrat, Republican, Independent. And we might observe a bunch of men and women who group themselves into these 6 cells. For this, we can create a null distribution exactly the same way, calculate a chi-squared in exactly the same way, and that's a really helpful first thing to do, because if we do it, we can conclude that there actually is a significant difference between men and women when it comes to party affiliation, since the p-value in this chi-square test is very, very small. However, we can only conclude that at least one of the parties is preferred to a different extent by men and women. So only one of the 3 pairs has to be different. We don't know which it is, and we don't know if it's more than one. So we need to run post hoc tests. In these post hoc tests, we need to reduce the table to multiple 2x2 tables, because if we now run a test saying, well, is there a difference between Democrats and non-Democrats and men and women, we can answer the question, well, is it different for Democrats, Independents and non-Independents, Republicans and non-Republicans? We need to run 3 follow-up tests to get the full picture. Because we don't need to do this manually, we can automate it, for example, with the very small additional R package, chi-squared post hoc test. Since it's a new package, you likely have to install it. In any case, you will have to load it with the library function before you can use it. And then this actually requires the data in a table format, so you need to run the table function. And then we're good to go to get the pairwise comparisons. If we run this command, we get the results of the 3 tests I just mentioned: Democrats against everyone else, Republicans and Independents. And we can first look at the p-values. And for the p-values we see there's a difference between men and women in how much they identify as Democrats and Republicans, but not Independents. And then we can look at the residuals to get an idea of the direction and of the size of the effect. So we can see that for Democrats the residuals for males is negative, which means we observe fewer males who identify as Democrats than we would expect under the Null-hypothesis. Conversely, for Republicans, the residual for males is positive, so we observe more males who identify as Republicans than we would expect under the Null-hypothesis. These residuals can also give us an idea of the size of the effect, so we can see that the 2 effects are roughly of a similar size. However, they are not a standardized measure of effect size. So if we actually want to report how strong the association between gender and political identification is, we need to look elsewhere. One place to look might be Kramer's V. It's quite similar to a correlation coefficient. It's a standardized measure of an effect size. It also needs an extra package in R, but then it's easy to calculate. However, it doesn't tell us all that much. There's no very good intuitive explanation for it. I'd encourage you to use it if you need to quantify the strength of an association between two variables with many different categories, because then there's nothing better. Whenever we are interested in specific categories, calculating odds ratios is a lot more helpful. Because when I now tell you women are more likely to identify as Democrats than men are, your natural question would be, how much more likely? That's where the odds ratios come in. So how would we figure this out? Well, we can't figure it out if we have more than two categories for either of our categorical variables. So we need to get rid of a category. Right now, we're very simply doing it by leaving out independents. Of course, we could also add up independents and Republicans, depends on the precise question we want to answer. But if we leave them out, we now have a 2x2 table, and we can figure out how much more likely women are to identify as Democrat rather than Republican when compared to men. So, firstly, what are the odds for women to be Democrats rather than Republicans? Well, you can just divide the number of female Democrats by the number of female Republicans. So there are about 1.5 times as many female Democrats and female Republicans. The odds for men are much closer to 1. But now what we're actually interested in reporting is the odds ratio. And for that, we just divide the individual odds. And we can report that in fact, women are 1.55 times more likely than men, or 55% more likely than men, to identify as Democrats rather than Republicans. So these odds ratios are something that has a very intuitive meaning. Of course, there are packages to calculate it. You don't need to do it by hand. It's quite straightforward to actually do it by hand. And at least you should understand where the figures come from. So, this much about using a chi-squared test to figure out whether two categorical variables are associated with each other. There's one more important use of the same test, which is called the goodness of fit test. So far, we try to see whether observed counts across a combination of two variables deviated from expected counts. But that also works if we only have a single variable. In there, usually, it's not so interesting to test whether the variable is evenly distributed, but whether the distribution follows some expected given distribution. Some set of proportions, for example. You can quite often use it to validate a sample. So if I sample people randomly, then various categories in my sample should be distributed in line with the distribution in the population. So I might say, well, I have people with these different employment statuses in my sample. Does the distribution of people across those categories deviate significantly from the known distribution in the population? One case where this might be good to emphasize an important argument is if we wanted to look at the youth prison population in the UK. So there we can observe how many young people are actually in custody. We can say, well, the expected, naively expected distribution would be that this is in line with population shares. Now we can use the chi-squared test to see whether the data we observe is unlikely to arise under this assumption, under the assumption that the shares correspond to population shares. For that, we need to specify the data, and we need to add the expected shares to the chi-squared test command, and we get a result that actually there's a big difference between the expected shares and our observed shares, so we can reject the null hypothesis and say some proportions are clearly different from others. Looking at the data, it's obvious what one of the proportions is, two of the proportions, more black people than expected, fewer white people than expected. However, to actually do post hoc tests and figure out whether the other two categories are also significantly different, we would need to do some more tests. And in this case, there's no obvious way to do it with an integrated function. So it would probably have to be done manually by just testing any pair of a specific category versus everyone else. An important thing to just remember here, like whenever we do these kinds of follow-up tests, post-hoc tests, is that we need to do some kind of alpha correction. We need to make sure that we don't inflate our false positive rate. Easiest would be the Bonferroni correction. We had 5 groups. If we now compare each of those groups against all the other groups, we have 5 tests, so we would need a p-value of 0.01. Anyway, that's as one other use for chi-square tests. A couple of conditions to be mindful of if you want to use these tests. One important one is that we need to have independence of observations. So no two data points should be related to each other. That, of course, excludes repeated measures designs. So we can't ask the same person for multiple ice cream preferences. But it also excludes paired observations. We can't ask a couple, we can't ask siblings. In the case of repeated measures, there are other tests to use, particularly the McNemar's test. In the case of paired or otherwise linked observations, we usually have to throw away some of the data. So there are quite a few published studies that somehow interview couples and then randomly select one of them for inclusion into their analysis. We shouldn't have sales with expected count below 5. So actually the ice cream example was problematic, probably had a sample that was too small. So try to increase your sample size, but at least make sure to use the simulation to estimate the p-value. If you use a simulation, you're much less likely to get false positives. However, you are realistically not very likely to find an effect with a very small sample. And lastly, the data used for chi-square tests really needs to be counts data. You can't input percentages, odds, or anything else. Quite often, you can get from percentages to count data, but just make sure that the data is in the right format for the test. Okay, so what to remember from this video? Firstly, just the key point, the associations between two categorical variables need a different test than all the linear models we looked at so far. If you're curious, I'll post the link below the video where you can find an explanation for how chi-square tests are actually just very special cases of linear models. But in reality, let's treat them as a separate way of testing this particular, answering this particular statistical question. To do that, we need to calculate this chi-square test statistic and compare it to the null distribution. We can use the chi-square test function in R and with a small sample size. In particular, we need to simulate the p-values. It's important to communicate effect sizes, and the easiest way to do that is by calculating odds ratios. They are about as intuitive is unstandardized regression coefficients. And we want to be able to tell people something that they understand. So, an unstandardized regression coefficient would be saying, well, if you're 10 centimeters taller, you earn on average 500 pounds more. An odds ratio would be saying, if you are a man, you are 20% more likely to be in some kind of management position. Completely made up numbers, but those are the kind of effect sizes that we would want to calculate because they're good to communicate. And then finally, the chi-square tests can also be used to compare our sample with an expected distribution, expected proportions. That's called goodness of fit. It also comes up in some more advanced statistical methods where we're actually trying to figure out whether our data fits some hypothetical statistical distribution. That much for now. As always, we'll practice this in class, and please do bring any questions that you have. See you there.